All right, hello. We're going to go ahead and get started on your chapter 7. What we're going to talk about today is arrays, how they work with a reference or a pointer type variable. We're going to talk about two-dimensional arrays and how they kind of extend your single dimensional arrays. And then we're going to get into what your book does do a good job of. Mostly when you're learning about arrays, they don't show you how to do object-based arrays or an array of objects. And so we're going to get into that. Then finally, we're going to talk about the array list, which is just what we call a linked list in other languages. And why is a linked list needed? So I'm going to use that term interchangeably, array list and linked list. So why are they needed compared to arrays? And that's because arrays have some limit or has a specific limitation. They're fast, but they're limited. So usually what you'll do is you will create this array all in one line, like so. But you don't have to, because there's actually two steps that are happening when you create an array. First, you're declaring the pointer of the array. And then you are saying, hey, operating system, go find me 12 bytes. That means an integer is 4 bytes, and you want 3 of them. So you say, go find me 12 contiguous bytes, which means just bytes in order. And then it assigns that first byte to be stored in our numbers reference. So let's get on the whiteboard and let's first talk about this first line. And that can be represented with a box. I've got it right here. This is kind of your number here that we have, and number, little chicken scratch there. But it's a 4-byte reference, and let's say that it's on the stack, so it's automatically assigned on the stack. It goes to, say it's at address 2000, it goes to 2003. But the main thing about this guy is what it stores, because what it stores is going to be the pointer to your actual 3 contiguous integers that represent your array. So when you have an array, you're actually using 4 bytes on the stack just to point to it, just to reference your array. And the array itself is going to be contiguous blocks of memory on your RAM. So this line 23, when you say we want a new integer but 3 integers, so that's what's saying, hey, go out and find me 12 unused bytes on the heap, and send me back the first byte so I can reference that with my numbers variable. And what that then does is it goes out and let's say that you're asking the operating system for 12 of them. And this is driving me insane. All right, there we go. Scribbles aside, let's see if I can even fix that, but that's fine. Just ignore those scribbles. So this is our three integers that we're going to have that we're asking for. And so the operating system says, okay, I found you 12 bytes that are in order. So the first byte, let's say that starts at address 3000, and from 3000 to 3003 is our first number. That's going to be our first integer. And then the contiguous part comes in where, because these are a block all together, then the next number of our 3 integers is going to start at address 3004. And it's going to go to 3007. And I'm just making these numbers up. They happen implicitly, automatically. And then the last one, of course, is going to be stored at address 3008 in your RAM, and go to 3000, whatever. 4 bytes more than 3008. So what is actually stored inside of our pointer is the address 3000. So all you need is the pointer to that first byte for you to have access to all 3 of your integers that are in contiguous memory blocks. And then we can fill that up with numbers like 0, 1, and 2. And we would preferably want to do that with a for loop. And this is why I always refer to using for loops starting at 0. Always start at 0 with for loops, guys. Even if it doesn't make sense, you got to start at 1. And you think you want to start at 1 because when you have fence post errors, when you're trying to solve them, 0 is actually your number 1. It really is. And also, mostly for loops are used to access arrays. So that you do have a different way that they show you how to use to walk through an array using like a for loop. That is and your book starts loops at 1. Oh my gosh, yeah. Okay, whatever. So in any case, that's one of the first things I do is when I look at code is I look at the loops, and if they start at 1, I know the person doesn't know what they're doing. So essentially, this is how arrays are done. You set up a reference for them, and then you instantiate the reference using the new operator, and you say how many you need, and then you have access to those 3 integers. And so let's go ahead and go back to that. And we can now use those 3 integers. But let's first, before we do that, let's just put it all in one line because that's pretty much the way everybody does it. And so what we're going to do is we're going to do a for loop that starts at 0. It's less than 3. So this is kind of the way I always do loops. And that way I'm never messing around with fence post errors or off by 1 errors. I always say start at 0 and go to less than the amount of items that are in the array. And then I go I++. And that way when you have in your algorithm a fence post issue, because usually if you start at 1 and you have a fence post issue, you see all these weird -2 +2s in the code. and that's because they're fixing the fence post issue, but they start at 1, so they actually have to add or subtract an extra 1. It just becomes a mess. So usually if you start your loops at 0 and you have a fence post problem, you either do an add of 1 somewhere in your code or a subtraction of 1. It just keeps you, regardless of where you're at in your algorithm, with your offset or your offsets and your fence posts, to one side of the 0 or the other, it just makes it off by 1 instead of off by 2. And then of course we use arrays or loops to go through arrays. So this is going to be a simple loop that I'm going to just say that numbers of I equals I. So essentially I starts at 0, and I'm saying take numbers of 0 and assign it to 0. That's the first time through the loop. The next time through the loop, I goes to 1, and I say take numbers of 1 and assign it to 1. But we're going to use I to parse through the array. And we're using I to set the value as well. So then we got this right here where we go back to our whiteboard. This is, even though we're assigning at 0, this is location 0. This is location 1. This is location 2. Now let's do a +1, an I +1, and that would change this so it's storing 1, change this so it's storing 2, and change this so it's storing 3. So let's go ahead and go back to that code and make that change so that we just add 1 to every time that we assign numbers of I. So I'm just going to take this and I'm going to copy it and I'm going to paste it down here, and we're going to do an output of this. And then we're going to look at multi-dimensional arrays real quick, and then we're going to talk about ArrayList and why we need ArrayList. So the next thing that I'm going to do here is I just want to output. So I'm going to do a system.out.print, and let's do just do a print. Let's just do a print, and let's send in numbers of I, but let's put a little space in between. So we're gonna do, you know what, I don't want to start making it too messy. I'm just gonna do this. What this is going to do is just put a space after each print. And we can actually inject that in there, but whatever, you know, I think we can do a plus and add a space, because it'll convert that that numbers of I to a text and then add it to the space. But we don't need to go that far. All right, so then when we output this, we should have our numbers 1, 2, 3 that are printed for each I location. Okay, so we have our output 1, 2, 3 down here. So we've officially created our first array. We've talked about how the memory blocks are contiguous in order. We've talked about how references or the pointers point to the first byte in that block of memory. Now let's extend this to how multi-dimensional arrays are done. Your book actually kind of does pretty good on this as well. So we're going to go ahead and clear this whiteboard, and we're going to come back to here with a little bit more to it. So let's go ahead and go into here, and what we'll do is we're going to now add another, and we call this in other languages like C++, this would be a double pointer. But you know, that's not really kind of the way we want to do things here and talk about double pointers. And you know, basically what it means is it's going to be a reference that references a reference. Yeah, that's how it's done. So we just take the idea of what we just did a little step farther, and I'll kind of demonstrate that for you here shortly. But now what we need is we need something more added to our loop. So we will come back to this here in a little bit after we work with after we get in and play around with how this is done in actual reference-based behavior. So when we think of it as just a sequence of references, let's draw it out and so that you can see what's happening here. So this part right here, we can actually separate out. So let's just talk about what's happening right here. Basically, we're saying we have a reference that's going to point to another reference. But even though a reference that points to another reference, it doesn't really matter too much other than semantics. So when I talk about syntax and semantics, syntax is what you write, semantics is how you write it. So semantics is, you know, how we are writing this. We're saying that this is essentially a two-dimensional array. Even though, you know, hey, we know it's reference based, but so now numbers, and I'm just going to shorten it, num, is again just a reference. And it doesn't matter. There's nothing special to it other than the semantics, and what's going on behind the scenes is much the same, but it is a little bit different. So let's say that this is created at address 1000. And we want a 3x3 dimensional array. And so num is a two-dimensional reference, or a 2dim reference. So the way that we do 2 dimensions is we can have a reference that points to an array of references. And we just take the idea of what we talked about a little bit further. So let's just kind of get into that a little bit here. These guys all become now a reference or a pointer. And they're going to have their own address. But the thing is we're still saying, go get 12 bytes for me, but we're not declaring it here. Right here, we're just saying, hey, give me, you know, we want 12 bytes, but all we're storing is references here. So this is going to hold the references to actual arrays of 3. And let's say that this first reference, we still need to find a block of memory that's contiguous for our array of references or our array of pointers. So let's say that this one starts at 2000 and these are 4-byte references. All references are 4 bytes. So this one goes on to 2004 and this one goes on to 2008. So then that means then this guy is going to hold the reference 2000 and it's going to point there. Well, then what happens is these guys are going to point to 3 actual integers. So remember, we're having a pointer to a reference, but these guys are the actual integers that they're going to point to, and there's 3 of them. So let's say that here is the first one. I'm going to just do a dash here to kind of, the first one, let's say that's at address 4000. And so this guy points to address 4000. Here, I gotta write that a little bit smaller. So it points to that first guy. This guy is contiguous, and this one's 4004. But you see, this array is going to actually store the integers. And then this one is contiguous, and it goes next to 4008. So you see, for a 2-dimensional array, we use the first portion of the array is just an array of references that point to an actual array of integers. And we can store our 1, 2, 3 here. And then the next one, because a 3x3 is a 2-dimensional array, means that we want to store 9 items. So the next one goes and points to another array. Now let's say it is at address 5000. So we just add more to it. And let's say that we're going to store the number 2 at address 5000. Then we store the number 3, and that's going to go at address 5004. And then we're going to store, say, the number 4, that's going to be at address 5008. And you guys can probably guess what this is. Let's say that this is at 6000. So we're going to point to that address 6000. And at address 6000, we're going to have the value, say, 1. And then that's going to continue on to the address 7000, or no, 6004, excuse me, 6004, because they're contiguous blocks. And we're going to store the value 2 there. And then the last one will be, let's say we store the value 3, and that's at address 6008. So we can see that from our first reference, we can reference all 9 values that we're storing in our 3-dimensional array. A 3x3 array should store 9 values. A size 3 array should store 3 values. And if it's a 3 times 3 or 3x3, that's 9 values. So essentially, the first reference points to an array of references. And then each of those references point to the actual array of integers. There's 3 integers there. This next reference that is 4 bytes up points to the actual array of integers that are both also contiguous. And then this next one that is contiguous to 2008 points to the last set of 3 that are also contiguous, storing the other values 1, 2, 3. So this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Exactly what we need for a 3x3 array. So there's a lot going on behind the scenes of this one silly line of code. And that's kind of how your contiguous memory is built. Now, here's where we're gonna go ahead and fill this memory up and play with it. But before we do, I want to talk to you about the limitations of arrays. Here's where our problem is with arrays. We can't ask the operating system for just one more. We can't say, hey, operating system, give me one more block and go out and give me it from that starts at 2012. And then I want to store another pointer reference here so I can have a 4x3 array. We can't do that because there may be another process on the operating system that's running using that block of memory. Because you have to ask the operating system for a contiguous block, you tell it how much you want, and it returns to you the pointer of the first byte to it. And then it assigns your process to that block of memory. You can't just ask to add on to it. You have to create a whole nother array of 4 and then copy from one to the other to be able to add one more to this array. So you would have to say, okay, operating system, give me a whole nother 4 of those guys. And then you would copy this one over here, copy this one over here, copy this one over here, and then copy or add the new one you wanted. And that's very inefficient. What makes arrays efficient is the fact that these addresses are already set. But here's the problem with arrays. You can't add just one more. And that causes an issue. Let's say that we are creating an array that reads information from a machine, but that machine's amount of information that's sending to our array has no limit, or we don't know how big it is or how much information we're going to get. So it makes no sense. Let's say that we're having an array that reads all the words in a book. Let's not create an array that's a million gazillion bytes large just to hold every book in existence. That's stupid and very inefficient. So the problem with arrays, I mean, what makes them well and good is the fact that you can add just one more. Or no, you can't add just one more, but they're fast and easy to get around to the data in them. The problem is you can't add just one more. And that's where your array list comes in that your book talks about, which is what a linked list is. With that, it's kind of more of a dynamic on-demand memory. This we still refer to as dynamic memory because the user can decide, you can ask the user to enter a variable called m and n, and you can instantiate the memory based on what the user inputs for m and n. So that's still dynamic. But a linked list or an array list is more dynamic than that because you can continue to just add one more to the end. Forever, for as long as, for as much RAM as you have, not forever, but that's the idea. So for a two-dimensional array, we need we need to use a nested loop. And with that, we add in a nested loop called, we usually call it J. And you can just take this and put J here. J is less than 3, J++. And then let's put in our little scope thing, our hoo-haws or whatever. And then let's add the same thing. I'm just going to go ahead and copy this and paste it right here. And then this will be for when we print it. And we're going to print it in 2 different ways. And then we're going to go down and I'll probably take a little break. That'll be a blink for you guys. But we'll be going into the array list here pretty soon. Oh, wait, no, not array list. We need to create an object to have an array of objects. Primitive variables act a little bit different than an array of objects. So we'll talk about that. So I'm going to kind of glance by this, but what we're doing here is we're using I and J to walk through all 9 of these guys. So I would reference the location here in this box. This will be I of 0, I of 1, I of 2. Then for every I of 0, this is J of 0, J of 1, J of 2. And when I'm saying of, I'm talking about the subscript operator. So that would be something like, and when we did numbers of I, I'm talking about that subscript. Numbers of 0 is the location of the first number. In this case, it's the first reference. But since I starts at 0 and j goes through every I value for every goes through every integer for every I reference, we can use numbers of I, j here to assign values to every item in the array. So essentially, when the I loop goes, it starts at 0, and then it drops down into the j loop. So let's kind of look at that. And I'm going to just say I plus j here. Oh, no, you know what? Let's just assign it to j every time. That's fine. Oh, numbers. I keep doing that. All right. I'm going to go ahead and set up the breakpoint here, and then we're going to go ahead and walk through this. Why are you not letting me? There we go. Finally. Gee whiz. Okay, here we go. We've created our array of numbers, and I is now 1. So let's go ahead and look at let's add a watch here for I, so we can kind of keep an eye on it. Why are you not letting me a new watch? There we go. I. Say, okay, there we go. There's I. There. Okay, now let's do one for j as well. They should go on the automatic variables list, but let's just go ahead and specifically add I and j. Let's make sure that is j. Okay, so I has not been created yet because this line has not run. So that's why we're not seeing a value here yet. So as soon as I step over, I is created within the scope of the I loop, and it's assigned 0. So right now I is 0, and then immediately in this nested loop, we go inside, and we declare j, and j is 0. Right there, 0 and 0. So when we say numbers of I, j, we're saying numbers of 0, 0 equals j. So numbers of 0, 0 equals 0. So that means back in our whiteboard here, numbers of 0, 0 is, well, this is the 0 location. This is the 1 location. This is the 2 location. This right here, for all these integers down here, this is the 0 location. This is the 1 location. This is the 2. So we're saying numbers of 0, 0 equals 0. Okay. Then we continue with our program. I do a step over again, and the j loop keeps running. I is still at 0, guys. The j loop keeps running, and now j is 1. It's been increased by 1. But I is still 0. So we're saying numbers of 0, 1 equals 1, because j is 1. So what we're saying is numbers of 0, 1 equals 1. So let's scribble that out and put a 1 there. Okay, we got a 1 there. All right, now let's go back to our code, and we run this again, and j is still running. The j loop is still running. It's going to run one more time, and j is going to be 2 now, so we're saying numbers of 0, 2 equals 2. So we'll go back over to here. Numbers of 0, 2 equals 2. And now things change. And we're just going to go through the first part of it because I'm sure you're kind of getting the idea right now. the J loop is done running because J is now going to iterate to 3, and it's no longer going to be less than 3. So it's going to drop down. Your runtime is going to drop down, and it's going to go back to your for loop for I. And I is going to run its next repetition. And so one is added to I. And so now when we run again, I is now 1. Look over here. Here's I. J is going to be created and rebuilt and remade because it's going to wholly run again starting at 0. So now I is 1 and J is 0. So we're saying numbers of 1, 0 equals 0. So we go back here. Numbers of 1, 0 equals 0. Okay, we go back to our code, step over, and J increases by 1 again. I is still at 1. So now we're saying numbers of 1, 1 equals 1. Numbers of 1, 1 equals 1. And then J runs again, and this goes to 2. J finishes running, and now we come back to I, and I goes up by 1 to 2. And it starts all over again. We go to 2, and now our I is at 2, our J is restarting at 0 again. And the J runs all the way through 3 times. And essentially what ends up happening is we get our 0, 1, 2 added here for this 2 location of I. And, hey, with a 3-dimensional loop, if you do a 3 by 3, you just take this whole thing and copy and paste it out here twice, and now you have a 3 by 3 by 3 pointer, and you have another reference point out here. So you have a pointer to a pointer to a pointer. So you just take the idea further with multiple dimensions. I will tell you one thing, if you're doing more than 3 dimensions, you're probably writing bad code. Mostly there's a better way of doing it. So that kind of gives us an idea of how this behaves. And once this is done running, we've assigned values to everything, and it drops down to our loop that we're going to use for printing. Okay, so let's go ahead and stop this, and let's look at what we're going to output here. What we're going to output is I'm going to do a print numbers of I J. Then inside of the J loop, I'm also going to put a space after each number is printed. Because this is, it's going to go a little bit backwards than the way we're visualizing it in my drawing. We're going to actually print it across the screen. If I can get this thing, we're going to take the array and print it across the screen, 0, 1, 2. We're going to print it across the screen like this. Excuse me. It looks like, yeah, okay. We're going to print it across the screen with this guy starting here, this guy right here starting a space starting there. Then this guy we're going to print here. Then we're going to put a new line in, and we're going to go to this guy and print it down here. Then we're going to go to this guy and print it down here. Then we're going to go to that guy and print it down here. Then we're going to do a new line, and then we're going to print this guy here, this guy here, this guy here. So we're kind of doing it a little bit opposite, then because we're going down here, we're going to left to right here with these guys. So that's why I'm putting a space in here. So here's going to be the problem is I'm putting a space. I'm going to have 9 numbers. If I run this right now, I'm going to have 9 numbers all output all on one line. 0, 1, 2, 0, 1, 2. So there's my 0, 1, 2, 0, 1, 2, 0, 1, 2. What I'm missing is right here, we're going to inject a \n inside of the output stream. And what that'll do is it'll force a new line. And then we'll have our rows and columns. Like so. So the reason why we do the \n out here is because the first line, we're just going through all the j's. Then I iterates and we go through all the j's again. Then I iterates and we go through all the j's. So every time I iterates, we want to do a new line and then print all the j's that are, the j arrays, or the arrays based on the j subscript. So this is arrays, guys. The last thing that we need is talking about how arrays of objects are a little bit different. For that, we need to just create a really quick object. Let's steal one from another. Let's see. Should we get no? Let's get leg. Let's get leg from our last thing. So I wonder if I can just. This is very dangerous to do, by the way. Doing your file moving around within the IDE, the Integrated Development Environment. I've actually lost like 6 months of work once doing this. So I would suggest that you guys do this in the directory, but I'm cheating. So what I'm going to do is I'm just going to copy that leg and bring it down here and paste it. Paste it into refactor. Copy? No! I just want to paste it in here. Why won't it let me do it? Okay, maybe just paste. Oh, crap. I got to drag it down. Okay, it's not letting me do that. Let's do it the proper way in the directory. Let's go ahead and go into where I have our chapter 7, chapter 6 code, where I have the leg. Let's go to where is the leg? It's probably in source. Chapter 6. There we go. There's our leg. Control C. We might have to do some messing around, but we're actually doing this proper way, because if you do start doing file moving and deleting within the IDE, you will screw something up big time. So let's do chapter 7. Java. Let's do that. Leg.java. We may need to add that somehow to the sources directory or move it around a little bit. But now when we go to our chapter 7, NetBeans should have gotten it for us. But here's what we got to do is we got to put it in the same package, basically the namespace. So it's going to be chapter 7 here. Okay, now we got our leg ready to work with. So let's make an array of legs. So it's going to go here, and what we're going to do is we are going to modify this number. And let's make a 3 by, no, let's just make, I'm just going to show you the legs simply with just one dimension, so you get the idea. Because what you got to do is, unlike an array of primitive values, you have to actually do a new leg for every value inside. For our primitive data, we didn't have to do a new integer for every integer. We just set up the pointers for them, and they went on the stack automatically. The integers, the 9 integers that we actually created, this is only setting up the references for it. Well, I mean, it sees that we're doing primitive variables and adds it, but on the stack. But with the new, we've got to actually, if we're doing an object of or an array of objects, we've got to do the new for each of those 9 integers that we had. Let's say that we're going to just do this for, we're going to call this legs, and it's going to be just a single dimensional array. We're going to have 3 of them. So what that means is that before you can assign a leg, you can't just say legs of 0 dot set or whatever, because it doesn't exist. we've got to actually do the new operator with that. So we've got to say legs of 0 is equal to a new leg. Like so. You know, I might need to take a break here and get this flushed out because it's being a stinker. Oh, duh. That's why I'm getting the stink from it. Okay. Well, you know, I'm getting a little ahead of myself. I want a leg array, a leg reference. The reference is still going to be four bytes, but it's going to point to a leg instead. And I want 3 legs. Okay, so and I'm going to call it legs, but we're using the leg data type. So legs of 0, we have to say is equal to a new leg because we can't just say legs of 0 dot got get length or whatever, or set length. Let's even try it. Let's set length of I. Let's just try and see that if that works. So let's run that, and we should get an error. There it is. So essentially what it's saying is because legs of 0 is null. It hasn't been created yet. That's because every user-defined object that you have, or any like traditional object, you got to actually instantiate the object that the reference is pointing to. So that's what a lot of books, when they start talking about object-oriented programming and arrays, they'll show you how to do it for the primitive values, but they don't show you how to do it for user-defined objects. It's not as easy because they do a lot of stuff for you with those primitive data types behind the scenes, and of course they go on the stack. So we've got to we got to actually instantiate the leg on the heap before we actually use it. So we're going to go to every leg that's in our legs reference, and we're going to say is equal to a new leg. And I don't know if I overloaded the constructor in there. Did I overload the constructor in this guy? Because we don't have to use the set. Yeah, I did. I said length. So we could use the set now. Let's just use the set because I started that way. But we could just send in the length there. But I can say now legs. So for every legs of I want to set the length. Why didn't you pop up like you should have? There. Set the length of the leg to I plus, let's just say I plus 10. Let's just say it's 10. Every leg of I is going to have the length of I, or the leg length of 10. And then let's go ahead and just do a quick system dot print. Oh, you silly goose. System dot, come on, yeah, give me some IntelliSense here. System dot out, yeah, okay. Print, and this should work if we overloaded the toString. We could actually just say legs of I. If we overload the toString, legs of I. We could just do that if we overloaded the output toString. Did we overload it in leg? Yeah, we did, right there. So that would work. It would just output my leg is whatever. We could also inversely do it this way. We could do something like system, system.out.print legs of I dot get length. So let's inject a new line here, and then let's inject a new line here, and then let's run it. So we should get a bunch of bunch of 10s. Let's see. All right. Why are you being a turd? Oh, it does not like me adding that. Oh, duh. I gotta do, yeah. Okay. Okay, so my leg is 10 long, 10. My leg is 10 long, 10, blah, blah, blah. All right, so this is the same idea of the integers, except for here's the thing. Every single integer, or not integer, but leg needs to be instantiated that's inside of your array. So that means that if we go back to here, and let's pretend that this is a leg, I've got to do, this is an array of legs, that's a 3 by 3 array of legs. I got to say new leg for this one. I got to say new leg for this one. I got to say new leg for this one. I got to say new leg for this one. New leg for this one. New leg for this one. New leg here, new leg here, new leg here. So for everyone other than the primitive data types, when you actually go to instantiate the memory, after you set up your references appropriately, you got to actually go through and walk through an array, the array with for loops, and instantiate each of these guys manually. And that's how you do object-based arrays. It's often better in a lot of ways to use an array list, but before we go into demonstrating an array list and how it's better, we're going to go on to array lists, but essentially the idea of an array list is so that we have that capability of adding just one more. The problem with an array list is you've got to start and go through each one that you have in your list. So to get to the last one in your list of an array list, you got to go and walk through each of the items up until that one. So we're going to come back and talk about array lists, and then we're going to get into some other fun stuff with writing some code. All right, guys, take care. I will be right back. Just a break time. Okay, we're going to continue on with our discussion on, this time it's array list. Now, it turns out that I was incorrect on thinking that the array list is a linked list. It looked and behaves like one, but it's not. And we'll talk about the ramifications of that and, kind of what a linked list is versus an array list and the behavior of them. So let's get into our whiteboard a little bit and talk about what a linked list is. So a linked list is a linked set of items of references, and to get to each item, they are linked together. And if you want one more, you can just link on another one. And so it's a chained list. So if you need to get to this item, you've got to start here and go through it to get here. Now, the difference between a linked list and an array list is just a dynamic memory that's contiguous as well. But here's the issue with an array list. So if you have an array list and you're working with your contiguous memory and you create an array list of size 3 and you want just a fourth one here. So what will happen is the array list, when it creates itself, it will automatically double itself. So it will have, when you create it with size 3, it will create itself so that it has more capacity. Now the issue being is what happens when you just want one more here after you go through your initial capacity. And what ends up happening is it creates a whole nother array list that's double the size of the previous list, and then what it does is it copies this guy over to here, copies this guy over here, copies each one over into the element, and then you have your extra one that goes beyond. You can add that then to that location. And then your capacity doubles in size. So that's where a misconception is on array list. Linked list is based on the linked list class that you guys can use. You guys will be actually doing that more in the next course that you guys take. So let's just concentrate on the array list because it kind of behaves like a linked list, but it's not. Okay, so let's look at playing with it. And because of that limitation, an array list is not as good as a linked list in just essentially wanting one more. However, what's nice about the array list that is, is the start of kind of working with you know, your own data types, is the fact that it uses what we call templates. And so some of the languages out there allow you to do this sort of thing. Let's go ahead and get into it. Where are we? Oh, geez. Oh, that's right, leg. Let's just close this stuff down because I'm starting to get a little bit too much going on. Let's go ahead and start just getting rid of just some stuff that we don't need to look at. All right, good. All right, what we're going to do here is we're going to have an array list of legs, and we're going to walk through it much like we did with our normal array. So the templating that you can have is you're going to declare an array list, and we're probably going to have an include that we need. Let's see how that works. Okay, so we're going to say we want an array list. Oh yeah, we got to import. Let's go up to import first. I'm pretty sure that we needed an import. Let's see. Let's do it right here. It'll yell at me if I'm doing it in the wrong spot. Import Java utilities dot array list. There we go. And that is our import. It's just yelling at me because we've not used it. Okay, now we're going to go up here and use it. We want an array list. And we're going to give it a name. My legs. Let's call it my legs. But here's the thing, is that we need to actually tell it what data type that we're storing. So here's where we will use kind of the templated type semantics. And right here is where I will say leg, because I want an array list of legs. And we'll say here a new array list, and it should look like this, something like this, array list. I'll probably have to do leg here. Now you don't have to, let's see, do we send it? I'm kind of referencing your book here a little bit. Let's see. No, we just have to invoke the constructor. All right, so that's going to create an array list which is just basically a dynamic array that's kind of hiding behind the scenes that uses some of the templates type capabilities. And this dynamic array has the ability to grow, but the problem is that when you do increase the size, it doubles and copies everything over. And that's where the inefficiency is. Now, versus the linked list you can just continually add on, but the inefficiency in a linked list is you have to go through each item to get to the last one. With an array list, since it basically is working with contiguous memory blocks, your arrays, it just doubles, copies over. So you can still just add one more, but at some point when you're adding one more, it's going to have to do create a whole nother array that's double the size, copy all the elements over, and then you've had the ability to add one more within the contiguous array issues. That is where the inefficiencies are with ArrayList, but it gets you beyond quite a bit of the problems, and you can actually build your own array list behind the scenes if you wish. But it also uses the templated type of semantics, which we declare what data type that we are going to store in the array list. And then we start using words such as add. So let's think here. When we are doing an array list of an object, here's what I'm interested in looking at, because we should have to do the new here. We should have to do a new leg every time. But with primitive data types, you wouldn't have to. You would just add the number in. So what we'll do here is, let's just look at its behavior without the new. And what I'm going to do is I'm going to say mylist.add. And what we'll do is let's just do this. Let's create a leg, and equals new leg. Let's invoke this constructor and send 10 for the length. Okay, let's add a leg 3 times. So we're going to add the a leg 3 times. Oh, excuse me. In the loop 3 times, add the data type a leg. And you're like, Mr. B, what's this going to do with the copy constructor? How is it going to make a shallow copy versus decopy? We're going to find out. And then what we're going to do is we're going to, in between, we're going to change the value of my list of 0 dot set. Well, you know, we might have to actually work with it a little bit differently here for the subscripting. Yeah, we got to use get. Can we do a get? We could probably do a get and set. You know what? Get index 0. Yeah, we're going to have to do new, definitely. So every time through, we have to add a new leg. And this is only for objects. You're going to have to actually instantiate a leg every time through. So what we can do is we can essentially just define the pointer, but every time through our loop, we create a new leg and we add that new leg that we've created onto the list. And let's say that we're going to add a length of I for each one. And then we have the ability to get that data type and then print the data. So here's what we'll do is down here, we're going to output each leg that we've added to the list with the get function of the array list. So I'm going to say my list dot get location I dot get length. So it takes what you returned, which is the actual leg at that location, and then we can run get leg. What we could do is we could say leg here, temp leg, and we could say here temp leg equals my list dot get location leg at location I, and assign it to the temp leg each time through, and then use temp leg dot get length here to output that value. So that's kind of what we're doing is a shortcut. Let's go ahead and just run it. We should see the value 0, 1, 2 output here. Here's our 0, 1, 2. What we could do is we could say, hey, let's just run this, and instead of assigning it to a temporary leg, let's just assign it to one that's kind of out there in the void, and let's take what is returned from the get function, and what we can do here is copy this, paste it, and instead of using that temporary variable, just say, hey, what's returned? Instead of temp leg dot, we just use the get function and then add the dot. And then you got get length. So that's kind of a little shortcut that you can do. You know, just kind of wrapping your head around it. I wanted to point that out a little bit. So let's go ahead and run this, because now we don't need templating, but that's just a you know, something. So what happens with the set function? So what you can do is we can say my list dot set, and then what we want is we're going to say go to position 2 in the list, which is the last one, and then we send it a new leg. And this is when we can do a shortcut on this one too. We can just say new leg of 200. It's kind of cool that you can just do stuff like that. When you build a leg and start working with like the new operator and stuff. So what it'll do is it'll send the reference of the byte reference of that new leg to the set function, and you'll have that new leg now in your set, your ArrayList set. So let's run it and see, we got 0, 1, 200. Okay, so just to kind of do a backswing, ArrayList is not a linked list. It is a dynamic array that doubles itself and copies itself over, and it does that all behind the scenes so that you don't have to deal with it. You do have to work with the get and set functions to do things with it. When you use your own user-defined data type, you must put a new leg on every item in the list, or it's just going to do a shallow copy of a leg that you've created. So if we don't do a new leg here, we're just going to be adding the same leg every time through the list. So we're only using the reference to hold each new leg through the loop, but each new leg is a full copy of a different leg that we're adding to the list. And that is key. You know, you probably wouldn't need this step when you're working with primitive data types. And I don't know, you know, your book may or may not show that. But I've shown you how to work with the ArrayList and objects. Let's go ahead and move on to the next bit that I wanted to talk about and go through, which is just having some fun. So I'm going to go ahead and go to a part 2 video where we're going to actually do an assignment, and then that'll be it for this module. Thanks, guys. Bye.